Hey, welcome back. So we are working on section 2 still, working our way through here. We just passed the halfway point, I guess, technically. So section 4, subsection 4, is all about modeling linear functions. And if you're keeping track of things, you might notice that this is a very similar title to subsection 3. Subsection 3 was constructing linear functions. So Mike, what is the difference? So usually when we say modeling, what we mean is something involving word problems, something involving translating English into math and then making something out of that. So when we say modeling linear functions, typically what we mean is there's going to be some kind of written description and we're going to have to make a line out of that. That's what we're up to. So our learning objectives for this are to model a linear function, which is fit to 2 data points. And we're going to also work on interpreting the slope of a line in an applied context. So because slope is kind of this really, quintessential feature of a linear function, we're going to want to make sure we not only know how to compute that, that's very valuable, we've been working on that the last couple of subsections, but also how does a slope get interpreted in one of these word problems, basically. So the one big example we're going to try to work with here looks like this. So we can just read through it and try to get a sense of things. So we have a biological model. This is there's a little footnote there because there's an actual link to the science journal that this data came from, so that's fun. It suggests that growth speed, which has a very interesting unit, in this case, molting periods per day, but all right, we'll work with it. So the growth speed of a nymphal aphid is a linear function of temperature. Nymphal aphid sounds like a great band name, so hit me up if you want to start one, although I have nothing to offer musically, so you're going to have to carry the band, sorry. So data suggests that at a temperature of 45 degrees Fahrenheit, the aphids have 0.01 molting periods per day. So not a lot of molting, not a lot of shedding their skin. And then when the temperature rises to 60 degrees Fahrenheit, the aphids experience more, so 0.175 molting periods per day. Okay, so the most typical response I could imagine. So you pick some random human being and you ask them to read those, 4.5 lines of stuff. They reach the end of it and they have no idea what just happened. What did I just even read? That is a totally understandable and acceptable reaction. And the solution to that reaction is to read it again, to go back and figure this out, because there's so much information packed into this, right? There's so much expected of us. There's lots of data, and just reading your favorite novel, you can kind of go through that because it's very easy to assimilate that information. It's not easy to assimilate this information when it's dense like this. There's a lot of information. The other thing I would argue is that if we stop reading here, that is, before there are any of the parts of this problem that we're going to explore, the questions we're being asked, then part of the natural human confusion is, what am I supposed to do with this information? What is the goal of it? Because by the time you reach the end of this, there hasn't been a goal. This has been purely informational. Great, I know some things about aphids, I guess. But what I would say is, let's read this first question and at least figure out, what are we trying to accomplish here? What am I supposed to be using this information for? So the first piece of information here, or the directions here are, find a formula for the aphid's growth speed as a function of temperature. And one of the things I want to do right off the bat is just note that this phrase is a super common one. We're going to see this over and over again this term. And one of the nice things to unpack from this phrase is that the first thing that gets mentioned, this is supposed to be our output variable. So this is what we're measuring as the output of this function. And then the temperature, or whatever it is that comes second, but temperature in this case, is the input variable. And then they're saying we're supposed to make a function out of these two things, with growth speed as the output and temperature as the input. So let's get that cataloged. So we need a formula. We're going to get a formula, and so far it looks like we're just repeating the line, but for growth speed, we can pick whatever we want. Nobody has forced us into a particular output variable here. I guess maybe I'll pick S for speed. Doesn't really matter. And this is some function. I can be lazy and call it F, I suppose, of the input variable. So we could use little t here. I'm going to use big T just to annoy you. No, not just, but it's always nice to kind of vary our variables whenever possible. I guess that's why they call them variables. Anyway, So we've taken some of this English and turned it into math. So here's where I would argue maybe it would be most productive to go back and do another read through. If I weren't doing this on my own and just trying to instruct you, I guess, you might, it would be perfectly reasonable before you look at this part A to read through this opening paragraph a couple, 3 times, just to see if you can kind of wrap your brain around what it is that's being presented to you. And then when you look at the actual goal, maybe this will make more sense going back through. But at the very least, now we can have another run through and say, okay, so we have this biological model. It suggests that growth speed, and that's kind of where I want to pause, because growth speed is the exact same thing that we just ran into down here. Whenever we've got references like this, where whatever variable it is, even if I don't understand what it is, how many gobbledygooks per zawad, like, I don't know, but if it's the same thing between one piece of the problem and another, it's referencing the same variable then. So these are our units, which are weird, but again, manageable. As long as we can copy it, we're okay. So the growth speed of this thing is a linear function, and I really want to get at that piece of terminology, of temperature. But while I'm on this color, let's connect those two pieces. So here it is. Growth speed is a function of temperature. Growth speed is a function of temperature. Super. So we're matching things up to what our goal was originally. Okay, so then as far as our, let's pick some different color here. So here is the piece I kind of glossed over is actually super important, or super useful to us. Not only are we trying to get a function, we're being told it is a linear function. So let's start cataloging the stuff that we actually know. We know that f of t, there I go using lowercase again, f of t is in fact linear. And so what that means is we have a custom-made template all set up for us that deals with linear functions. It's some constant times whatever our input variable is, capital T in this case, plus some constant. And that is, oh, it's just amazing, because without that one little word here, we would be totally stuck. We'd have nowhere to go with this problem because we wouldn't have a basic formula template to begin with. Okay, so continuing on our merry way, maybe not so merry, we've got more information here. So data suggests that at a temperature, and as soon as I see the word temperature, alarm bells go off, because I know that's one of these variables we're measuring. I know now we're talking about, whatever is about to happen is talking about this input variable. So temperature of 45 degrees Fahrenheit, boom. So that orange does not look different enough. Adobe, you have failed me. Okay, so maybe we'll try red there. So 45 degrees Fahrenheit, and that is paired with a value of 0.01 molting periods per day. And so what I'm going to say is, look, this has given us one great piece of information. It's told us, so in addition to knowing that the f of t is linear, we also get that when capital T is 45 degrees, then what is it? Do we use S? That S is 0.01. So capital T equals 45. That's going to imply that S is 0.01. Another way to write that is just to say that when then that we have the point on the graph that looks like 45 for the input and 0.01 for the output. We got to be careful here, right? You got kind of a 50-50 chance if you just guess, but the 45 went in that first component. It's like our x value, if you will, because temperature was the input variable. So input variable gets first spot in these points, and then the S was 0.01. I definitely see this swapped sometimes when we look at like economics problems where there's like a price and a quantity, and you could sort of imagine those being in either spot. But because they forced us into growth speed as a function of temperature, that sets for sure growth speed is the output thing, temperature is the input thing. Okay, we've got one more point that we can kind of tease out of this last sentence. So when the temperature rises to 60 degrees, the aphids experience 0.175 molting periods per day. So that's another pair just like the one that we came across. Okay, I think we'll be able to move. T equals 60 implies S equals 0.175. Or the point 60, 0.175 is on this graph. Great. Okay, got arrows going everywhere. Oh, maybe I can add in this little arrow for the linear piece, but who knows? We'll see. Okay, so we've got, I would argue, we have both extracted every last little bit of information that we can out of this paragraph and have enough information to make some progress on this goal to get a formula. So just to recap what we've done, we took the 4.5 lines plus, the one line of our target and turned it into this. We want a formula, S equals f of t. We know three things basically that are useful. We know that f of t is linear, so the formula must look like this. And then we have 2 points that have given us enough information to kind of get started. So our typical approach to finding the formula for a linear function is to first get the slope. If it wasn't given to us, let's figure it out. So in this case, slope, that's our constant a here, looks like difference in the outputs and difference in the inputs. Doesn't really matter what order we go with. I don't know, if you think of this as the second data point, maybe we put that second, and then we're taking away 0.01. And then similar deal, as long as the pairing goes in the same order, you can start with whatever point you want. But since I started with 0.175, then the thing on bottom that comes first has to be the input that went along with it. So 60 and 0.175 are paired together, 45 and 0.01 are paired together. I think with a little calculumentation, a little math magic, then we're down to a slope of 0.011. And if you're asking yourself, which you aren't, but I'll ask it anyway, hypothetically, Mike, what does that slope actually mean here? Well, that's actually our next question. So once we get our formula, we'll be asking that exactly. And now we're down to finding some constants. So we figured out what A is. We've got one constant left, and that is the value of B. So here's what I would recommend. We used one of our points. It turns out it doesn't actually matter. This is a little bit creepy because the arithmetic, like the solving process, looks totally different if you use the 60, 0.175. All the stuff in the middle looks different, and then you end up with the same B value that we're about to get. So it's kind of wild, but math has its mysteries. But the goal is, the hope is, it shouldn't matter what point we use, the constant B ought to be constant no matter which point we use on this line. Okay, so we're going to start from our formula. We've got f of t is a times t plus b. And then now we have, there's like four things here, right? There's f of t, the output. There's the constant a. There's temperature. And there's the constant b. We know three of these things, at least for the moment. We know an output looks like 0.01. Not always, but for this one temperature, that's definitely the output. We know the slope is always 0.011. The temperature that got us there was 45, and now here's B. So if we take away this 0.011 times 45 from both sides, we get ourselves a value for B. That looks like kind of a mess, but it's not an awful number. I think it's 0.485 that we come up with. So it turns out we've done it. We've got ourselves a formula. And really, it's just the victory lap at this point. It's tempting to stop, but we needed a value for A, we needed a value for B, and then if you look back at our actual goal, it was get a formula. So we've done all the legwork to get that formula, and now we just have to actually put it together. So this f of t is A times t, and then it's plus B, but since B is negative, I'm just going to write minus. And, well, if anything deserves a victory box, then this certainly does. But so let's give it one. Just a quick note on this. Remember, we went back to capital T here because what we want is a recipe. We want to have an input variable and an output variable, and the things that go into our formula that don't change are simply those two constants. We used 45 over here, but that was just to help us figure out what B looks like. The temperature is not always going to be 45 degrees. So this is a formula that says if you wanted to know how quickly are the aphids molting, which I guess is a measure for how much they're growing, because if they shed more skin, it's because they're getting bigger. That you tell me the temperature, and I can tell you how many molting periods per day they will have based on this formula. So, kind of cool if you care about aphids. Part B. What does the slope of the function represent in the applied context? Okay, so just as a reminder, the slope we came up with was this number up above, this 0.01. We used it a couple of times here. And so our slope was 0.011, and our goal is to basically to write a sentence that says what this number actually means. So for one thing, let's say for as far as units, the units on the slope always looks like units on output divided by the units on the input. So in this case, it's a little bit weird, but that's why we have this nice setup that will always be the case. So our output was this growth speed thing. So this is molting periods per day. And so there's our entire numerator, which is already itself kind of a rate, right? Molting periods per. Whenever you see the word per, you're thinking like a rate of some kind. And then the units on the input, this was temperature, so this was degrees Fahrenheit. This will be a test to see if I can spell Fahrenheit. Probably not. I think I spelled it up here correctly, so let's double check. Hey, maybe. It's certainly possible I spelled it correctly. Okay, so this is a weird set of units. Molting periods per day per degree Fahrenheit. Yikes. So it's not always the case. Sometimes this unit makes a lot of sense. Like if you're looking at demand or whatever, and you look at slope, that's like how many fewer items do you sell when you increase the price. So it might look like items per dollar or something like that, or dollars per item. So in this case, I'd like to kind of write a template to set ourselves up and try to get an idea of how to do this in general and then apply it to this particular scenario. So here's my template. So it might look something like for each additional one, and then we kind of want to play Mad Libs with this. Blank, blank. And so these two pieces are basically for each additional one, and then we're looking at input and our input units. And then we have some kind of output thing. And a slope is describing some kind of increase or decrease. So we have some output, and then, right, which of these options we're working with depends on whether the slope is positive or negative, whether you're headed uphill or you're headed downhill. And then, so output, or whatever that is, increases or decreases by whatever our slope value is. And then we need output units, which in this case I'm going to leave a little extra room for. I realize I'm squeezing it in here, so I apologize for that. So it's right. So for each additional one something that happens with our input, our output or increases or decreases by some value. Okay, so let's see if we can kind of fill in the gaps with our actual scenario here. So our input units, in this case, we've sort of been keeping track of these. So for each additional degree Fahrenheit, I'll abbreviate just for the sake of space. So for each additional degree Fahrenheit, the output, which was growth speed, so growth speed increases by the actual slope we had was 0.011, and then the units on that were molting periods per day, because that's what our output was measuring. Okay, for every so when the temperature goes up a degree, we would expect, oh, and I should probably circle, increases. So this is the case if a is positive, if our slope is a positive number. And then, of course, if we had the opposite scenario, which I won't circle, but I will identify, if a was negative, we would be talking about how this output would be decreasing. So that's not our scenario in this case, but certainly could come up. So growth speed increases by 0.011 molting periods per day. So temperature goes up, aphids are molting more frequently. That seems to make some sense. Who knows? I don't know if that'll hold forever, right? Presumably if you get to like 500 degrees or something, these aphids are not shedding their skin every minute or whatever. But mathematically, that's what our description comes down to. Okay, last question. What does the vertical axis intercept of this model represent? So we talked about slope, which is arguably the more important of these two interpretations. Vertical axis intercept, you could talk about any function this way. Every function that crosses x equals 0 has an interpretation like this. Only linear functions have a slope to talk about. So there's that. So what does this mean? Well, as a reminder, b actually is our vertical axis intercept. So this is taking on whatever b is tells us where this graph is going to hit our vertical axis. So here it's at negative 0.485. All right. So let's pick another little, I don't know, Mad Lib kind of sentence to go along with this. So when whatever our input is 0, and then we'll keep our units. So here's input, and then here's input units. And unlike up above where we had to sort of put in the numbers here, the 0 is going to be the case because that's what it means to be a vertical axis intercept, a y-intercept if you like. I'm trying to avoid x's and y's, as you might recall. But when the input is 0, whatever it is, the output is blank. So here is output, and then this is the value of b, basically. And then because we're trying to stay in context, here is output units. Lovely. So then we fill in the gaps with the world's worst Mad Lib. If you've ever played those, they should be funny. This is in no way funny. I apologize. So when the input, so this is temperature, is 0, and then in this case it's degrees Fahrenheit. So 0 degrees Fahrenheit, man, that's cold. Remember, that's below freezing, right? 32 degrees Fahrenheit is freezing. This is very chilly. The output, so our output was in growth speed, so for consistency I'll just put speed for short again there, but hopefully you know what we're talking about. And then B, so that was our negative 0.485, and that's output units was molting periods per day. So when the temperature is 0 degrees Fahrenheit, growth speed is negative 0.485 molting periods per day. What does a negative molting period mean? That seems odd. I don't know how you... Is that like packing more skin on yourself instead of shedding it? I don't know what that means. So this is a little bit of a giveaway, but is that interpretation meaningful? Yikes. If it had been a positive number, I think we could salvage something out of this, but the fact that it's negative really kind of challenges my understanding of this in a context. So maybe not meaningful is a reasonable way to go with this. Negative molting periods seems weird. That's the technical term, except that's not how weird is spelled. Oh, iPad, calm yourself. Okay. Yeah, so really, I don't know. There may not be... I don't want to say there's no wrong answer, but if you're explaining yourself on these, I'm generally happy. So this is the type of thing that will typically either be a multiple choice thing where the other options don't make any sense and you pick the one that actually is a valid explanation, or it's one of the ones on a test that we would grade more carefully and we would take a look at your actual response and see if your justification is good. So for instance, I could see somebody claiming that it is meaningful and they would say that a negative growth speed just means that the aphids are getting smaller instead of getting bigger. So molting periods maybe is a weird unit for it, but thinking about growth speed, a negative growth maybe just means that they're shrinking. So when it's really cold like this, maybe the aphids stop growing and instead start getting smaller. That'd be a great full credit answer to this question that is the opposite of what I've written, because they're saying that I'm saying it's not meaningful and that other person made a different claim. So all I'm really getting at is with the is this interpretation meaningful kind of question, your explanation matters a great deal. So you could have a completely different answer for me and still get full credit because you explained yourself well. Okay, not always possible. Math is not always that forgiving, but that's it for subsection 4. We'll be back with a little bit more modeling because I know how much trouble this can cause, and that'll take us to the next 2 subsections and the end of section 2. See you then.